All right, so we are going to move forward now. We just finished talking about chain rule and implicit differentiation, some big topics here. And now we're going to apply that into what we call related rates. Okay, and so this actually has a really practical application. And just to kind of illustrate how these will work, we'll do some very basic problems today, and then we're going to continue this. This is going to be several days worth of work with related rates. But so the background is this. Okay, really we don't need to know this, but let's just say, let's say we have a circle. Okay, and we know the radius is 4 currently. And now we also know dr dt. Okay, and without anything else given to us, you should interpret this as a rate of change with respect to time. In other words, the radius is changing at a rate of 2 units, whatever, centimeters, meters, right? 2 centimeters per minute, let's say, or 2 centimeters per second, or something like that. Okay, and so the whole point of this is, well, if this starts to increase, eventually it goes out to reaches 6 centimeters and then 8 centimeters, right? What we are going to be interested in now would be, well, how does the area change, right? As this radius increases at 2 centimeters per second, let's say, at what rate will the area change, right? And so that's essentially a related rates problem, and you can apply this in lots of different scenarios. But in order to figure these types of problems out, you use implicit differentiation and a little bit of chain rule and all the other stuff that we've talked about, like product or quotient rule, and you're good to go. All right? And so let's take a look at the first problem. We know the area for a circle is pi r squared. We know the rate of change is 2 with respect to time for the radius. We're interested in how the area is going to change with respect to time when the radius is 4. Okay, and so here's the key. We need to differentiate with respect to t. Okay, so we're going to take this equation right here, area equals pi r squared, and we're going to differentiate with respect to t. Okay, and so think about, so here's a variable. The derivative of a is technically just 1, but you have the chain rule giving you dA dt. Okay. Now here we have r as our variable. So think of this whole thing as pi r squared. What's the derivative of that? Use the power rule. The 2 comes out, becomes 2 pi r. And again, chain rule, you're going to do dr dt. Right? You're always going to apply the derivative of the variable that you are taking the derivative of. So that's where the dr comes from with respect to time. That's where the dt comes from. Over here on this other side, technically, we get a derivative of 1, right? And then, again, derivative of the variable that we're looking at, which is a, with respect to time. So that's dt. Okay, so hopefully that makes sense. And now, what I suggest doing is just plug in what we know. Okay, so they tell us that dr dt equals 2. So I'm going to replace this with a 2. So I've got that plugged in. We're looking for dA dt, so that's going to remain. And they do tell us that r is 4, so I'm going to go ahead and substitute that in here. So 2 pi times 4. And so we are practically done, right? It tells us right here that dA dt, the area will change at a rate of, if we multiply all that out, that's going to be 16 pi units per unit of time, centimeters per second or meters per hour or whatever the case is. Okay, so again, related rates, it's essentially you're given one rate of change and you're using that information combined with what you know about the situation at hand to figure out how another variable is changing. Okay, Another scenario would be something like, let's say we're conducting an experiment and we're keeping track of temperature and how the temperature changes with relation to how far away we are from a heating source or something like that, right? So you'd have two variables there, the temperature, and you'd also have the distance away from the heating source. And so you can play with one of those variables. For example, maybe I move the object away at a rate of whatever. So that would be like knowing what the distance dd dt would be. And then now you'd be interested in finding out, okay, so how will the temperature be affected? Okay, or vice versa, okay? But that's essentially the application of related rates. Hopefully that kind of makes some sense here, but again, here's kind of the basics. So let's just go ahead and finish these last three examples quickly. Same process. So here's our volume formula. We know the radius for the sphere here is going to be 3. And we also know this. dr dt is equal to 10. So let's go ahead and just apply d dt to the entire equation, to both sides. Since we need derivatives with respect to t, that's how I know to use d dt. If this were, let's say, ds on the bottom for both of these, then I would apply d ds, and it's the same process. Okay, but right now we have d dt. So now, again, the derivative of v is just 1, but then we multiply that with dv dt. And now take the derivative of this side. The only variable we got here is just the r cubed. So bring the 3 out in front and decrease the exponent by 1 using the power rule. Okay. And let's simplify it a little bit. These 3's cancel out. Oh, one major mistake here. Let's go back. So after I found the derivative, again, you have to apply the chain rule. Don't forget dr dt. Okay, every variable is going to get a rate attached to it, dv dt, and in this case, on the right-hand side, dr dt. All right, so we got 4 pi r squared dr dt, and now let's go ahead and plug in what I know. I know that dr dt is equal to 10, so I'll put that in over here. I know the radius is 3, so I'll put that in right here. 4 pi is good. And, well, this is convenient. I don't have to move anything around. I just figure it out. It tells me what dv dt is going to be. And so if I just multiply this out, we got 3 squared, which is 9, times 4, 36 times 10 is 360. So 360 pi would be this rate of change. All right. Example number 3.
For 2 students, this includes period 5. You should move.
Again, we're going to apply, since we got dt's, we're going to apply d dt to the whole equation. And if it helps, a divided by 6, it's really the same thing as 1/6 a, right? And actually, let's... Ooh, I messed up my notation here. Let's make that clear. So I'm going to start over. I'm taking d dt of the entire equation, not just the left-hand side. Okay, got ahead of myself there with the right parentheses. So I'm taking the derivative with respect to time. On the left-hand side, our variable is theta. So take the derivative of sine. The derivative of sine is cosine. And now, again, we're going to attach from the chain rule d theta dt equals, on the right-hand side, just look at that, derivative of 1/6 a. That's just going to be 1/6. But again, since our variable is a, don't forget to attach dA dt. And now let's plug in what we got. Cosine theta. We know theta is pi over 4. So I've used that. D theta dt, I don't know, so that's going to stay there for now. Then I got 1/6. And now dA dt is right here. It's -2. So now let's continue simplifying. The cosine of pi over 4 is root 2 over 2. Negative 2 times 1/6 is negative 1/3. And so this is finally an example where we're not just done, right? Like we actually have to get d theta dt by itself. So think back to algebra. We have to get rid of this constant. Probably the easiest way to get rid of a fraction is to multiply by the reciprocal on both sides. And so that's what I'm going to do. Cancel these out over here. And now we're left with d theta dt. And that's going to equal negative 2 over 3 root 2. Okay, these aren't so bad once you do a few of these. They're pretty important, so we're going to do several. Again, just learning the basics now. Right now you're given formulas. They're kind of right there in front of you, so it's not too bad. Eventually you're going to be reading problems, just like this one here, reading the problem and actually trying to come up with a lot of this stuff on your own based on what sentences and what descriptors there are for what is going on. Okay, on the back, we got problem number 4, example 4. Oh, this is a good one. Okay. So we're looking for dz dt. And so here's our equation, z equals 1/2 xy. We're going to apply d dt to the entire thing. And just to show the different ways that you can show this step, I'm actually going to write out d dt on both sides. Derivative of z is 1. Attach the chain rules dz dt to that, and you're good on the left. On the right-hand side, we have a little dilemma. We have a product, 1/2 x and y. Two different variables, x and y, and we're multiplying them. So we got to use the product rule.
Students,
okay?
please make your way into your period 1 class.
And so product rule, think of this as your f right here, and think of y as your g. Product rule, right? It's f times g prime plus f prime times g. Okay? And so if I write that out, f is 1/2 x. So here's f. G prime, the derivative of g would be just 1. But don't forget, chain rule gives us a dy dt to attach to that. Plus, and now we go f prime, derivative of the first function, times the second function. So maybe these quotes are confusing. Let's just cross those out. Maybe makes it easier to see. Right? First function times the derivative of the second plus derivative of the first times the second. So that's what we're doing here. So now we're looking at f, which is 1/2 x. The derivative of 1/2 x is 1/2. And then we have to attach a dx dt to that. And then don't forget, we still have that y there. All right, so now let's plug in what we know. We got 1/2. We know x is 8. dy dt is 3. So I've used that. Plus 1/2 times dx dt is -4, so I'm going to put that in. And now I need y.
Students, this concludes period
Uh-oh, they don't give us y,
Please make your way to your
but they give us
period
z.
7 class.
So we should be able to use this in conjunction with this and the original equation to work backwards and find y, right? We have a relationship between all three variables. They gave us 2 of them. It's not hard to find the missing one. Just use some algebra. Plug in z equals 20. You got 1/2 times 8 times y. This becomes 4y on the right-hand side. So from there you get that y is 5. So now we know that y is 5. You plug that in here, and then you have dz dt. So now you just figure it out. 24, half of that is going to be 12. Negative 20, half of that will be minus 10. So dz dt here is going to be negative 2. So z changes at a rate of negative 2 units per unit of time when these other conditions are going on. All right, so that's good enough for an intro with some basic related to rates problems. Hopefully that makes some sense, and if not, we'll go over some of these questions that you might have in class on Friday. All right, see you guys later.